Okay, so now we are learning about the concurrency. So by executing multiple threads, they share some resource. We can improve the performance by parallelizing the execution of thread, and we can utilize multiple computer system resource. But there are many problems in concurrency implementation. So many researchers have spent a great deal of time and effort looking into concurrency bug, okay, over many years. So many works focused on deadlock, okay, but while recent work focused on studying other types of common concurrency bugs. So that is called as non-deadlock bug. So in this chapter, we'll take a brief look at some example concurrency problems found in real code to better understand the problems to look out for. Okay, so what types of bug exist? So the first question is that what types of concurrency bug manifest in complex and concurrency problems? This question is difficult to answer in general, so but some researcher, so Lu at 2008, he studied about the many bugs type in real code. Okay? And so he analyzed a number of popular concurrent applications. So for example, MySQL, so very famous database server, and Apache is famous web server, Mozilla is web browser, and OpenOffice is office program. So Lu studied the bug types of this code, okay, and there were 105 total bugs. So among them, so non-deadlock bug occupies large portion. So there are only 31 deadlock bugs. So non-deadlock bugs make up a majority of concurrency bug. Okay, so non-deadlock bug make up a majority of concurrency bug according to the Luge study. So then let's consider what types of bug are these. Okay, so let's discuss the two major types of non-deadlock bugs found by Lu. So the first one is atomicity violation bug. Okay, so let's see this example. So this is my SQL code, a part of my SQL code. So there are two threads, thread 1 and thread 2. So thread 1 access proc info field of in the structure of THD. So it first check whether the proc info is non-null. Then if the value is non-null, it print out the value using fputs function. Thread 2 also access proc info. It set the value to null. Okay. So in this case, during the execution of thread 1, it first check proc info. If this is non-null, it will enter this if path. Then when before executing this fput string function, so there is some interrupt and thread scheduling. Then thread 2 is executed. Then thread 2 will set the proc info value to null. Then when thread 1 is resumed, then when it executes this code, this function will access null value. Okay, so this thread will crash. Okay. So the definition, the formal definition of atomicity violation is that the desired serializability among multiple memory access is violated. So that is code reason is intended to be atomic. So these two operations, so check and access operation must be performed atomically, but the atomicity is not enforced during execution. To solve this problem, okay, to correct this bug, so we must use mutex lock. Okay, so by protecting this critical section with mutex lock, and here is also with text lock and unlock, so we can avoid the atomicity violation bug. So to guarantee the atomicity of the critical section, we must protect the code with mutex lock and unlock. Okay, so another common type of non-deadlock bug is order violation bug. So here is another simple example. So here is thread 1 and thread 2. Thread 1 and create m thread, okay, and thread 2 access the thread state, okay. So here thread 2 seems to assume that the variable m thread has already been initialized and is not null, but if thread 2 runs immediately once created, the value of m thread will not be set when it is accessed within this main function in thread 2 and will likely crash with a null pointer reference. Okay, so the formal definition of an order violation is the desired order between two memory access is flipped. Okay, to fix this bug, we must enforce ordering using condition variables. So this code is fixed code. Okay, so thread 2, okay, must call the wait function for the condition variable empty cond, and this code is protected by lock and unlock. Okay, then after get some signal for the condition variable, it can access this m thread, and thread 1 and initialize, first create the thread, then it send the signal for the condition variable. Then the ordering between these two threads can be implemented. In summary, a large fraction, 90-70% of non-deadlock bugs found by Lu are either atomicity or order violation. And thus, by carefully thinking about these types of pattern, programmers can likely do a better job of avoiding them. Moreover, as more automated code checking tools develop, they should likely focus on these two types of bugs, as they constitute such a large fraction of non-deadlock bugs found in deployment. Unfortunately, not all bugs are easily fixable. As the example we looked at above, some require deep understanding of what the program is doing, or a large amount of code of their structure organization to fix the bug. Okay, so a classical problem arises in many concurrent systems with complex locking protocol is known as deadlock problem. So in this example, we have thread 1 and thread 2. Thread 1 has lock L1 and it is holding a lock and waiting for another lock, and thread 2 has lock and it waiting for another lock. Then when these two threads execute concurrently, this case can happen. Thread 1 hold lock 1 and it wanted to use lock 2, but thread 2 hold this lock and this lock 1 is wanted by thread 2. So there is a circular dependency between these two threads. Then, but deadlock does not necessarily occur, so rather it may occur. So when if thread 1 is first executed after completion of thread 1, if the thread 2 is executed, then there is no deadlock. Okay, so unfortunately, two threads concurrently hold their a lock and they are waiting for another lock, then the deadlock may occur. Okay. So in this example, how about if thread 1 and 2 both made sure to grab locks in the same order? So for example, we first acquire L1 first and next L2, then there is no deadlock. Okay, so this case cannot happen. Okay. So then why do deadlock occurs? So due to the complex dependencies between components. So for example, in Linux operating system, so memory page is accessed by virtual memory system and file systems. So virtual memory 2 subsystem of operating system will concurrently access memory page, and they also interact each other. So in this case, this shared resource access will generate some deadlock situation. So another case is encapsulation. Okay, so encapsulation is originally used to hide details of implementation and thus make software easier to build in a modular way. So for example, Java vector class and its method add all can be used like this. So two vector variables declared, and each vector can use the method add all, so it can use the argument of another vector. So in this case, internally, because the method needed to be multi-thread safe, locks for both v1 and v2 needed to be acquired. So this add all routine will acquire the locks in the same arbitrary order. So first v1 and v2. If some other thread calls v2 add all v1, then it will call lock v2 first, then lock v1. Then there can be some circular dependency, then this can generate deadlock. But this situation is hidden from calling application because this operation is encapsulated within the method. So the software programmer cannot recognize the deadlock situation. Okay. Okay, so 4 conditions are required for deadlock situation. So first, mutual exclusion. Okay, in this condition represent the thread claim exclusive control over resource that they require. So they will want to get a lock. Okay, so second condition is hold and wait. So this means thread hold resources allocated to them while waiting for another resource. They are holding some resource and they are waiting another resource. And so the condition is low preemption. Okay, so resources such as locks cannot be possibly removed from thread that are holding them. So if a thread has if a thread hold the resources, it will not release the resource. Okay, then last condition is circular wait. There exists a circular chain of threads such that each thread holds one or more resources that are being requested by the next thread in the chain. So thread 1 has L1 and it wants to use another resource L2, but thread 2 has this lock, okay, and you want to use the L1. Okay, so there is a circular chain in the resource allocation. If any of these 4 conditions are not met, the deadlock cannot occur. So to prevent deadlock, if we remove one of these conditions, then we can prevent the deadlock. So to prevent deadlock, prevent one of above conditions. So then let's discuss the deadlock prevention technique. So first, okay, let's consider the circular weight condition. So to prevent the circular weight, we can use total ordering technique on lock acquisition. So for example, if there are only 2 locks in the system, L1, L2, so you can prevent deadlock by always acquiring L1 before L2. If all threads follow this order on lock acquisition, there is no circular weight. Okay, but total ordering is very difficult to implement the total ordering in real system because there are many lock variables in the system. So partial ordering can be useful in more complex system. So for example, Linux file memory map code also use the partial ordering. Okay, so here 10 different groups of lock acquisition orders are provided. So the programmer, Linux programmer, must follow the partial order between the lock variables. So first, for example, first this lock must be acquired before acquiring this lock, and this lock must be acquired before this private lock and sub lock and mapping 3 lock. Okay, so by following this partial order, we can prevent the circular weight regarding these lock variables. And we can another technique is to enforce lock ordering by lock address. Okay, so by using this technique, we can solve the encapsulation problem presented in the previous slide. So for example, by comparing the lock address of 2 lock variables, okay, so the row address lock variable is first accessed. Okay, then we can make some ordering between lock variables. So this ordering requires careful design of locking strategy and must be constructed with great care. Ordering is just a convention, so any sloppy programmer can easily ignore the locking protocol, this convention, and potentially cause deadlock. So this slide shows the real example used in memory map code in the Linux operating system. So for partial lock ordering, so in this code, this lock ordering, so there are several partial ordering. Okay, so this ordering, and this one, and this one. So several partial orderings are specified in this code. So a Linux programmer must follow this partial ordering when he acquire the lock variables. But this is only convention. Okay, so this is not enforced. Okay. So next, to prevent deadlock, we can prevent hold and wait condition. Okay, so hold and wait means thread has a resource and it is also waiting other resources. So to prevent this situation, we can use the technique of acquiring all locks at once atomically. So to acquire many locks, so this code is protected by a prevention lock variable. Okay, so by using this technique, all locks acquisition can be performed atomically. Then we can prevent the hold and wait problem. But this is a drawback. We must know exactly which locks must be held and acquire them ahead of time. Okay, so and all the locks first acquired, then it can perform some other remaining jobs. So it can decrease concurrency as all locks must be acquired early on instead of when they are truly needed. Okay, so the concurrency between thread will be degraded by this technique. Okay, so this is the practical solution. Next, to prevent no preemption condition, we can use try-lock API. So this API attempts to grab a lock, and if it is available, returns success, but otherwise it returns error code indicating the lock is held. And the thread can try again later if it wants to grab the lock. Okay, so we can implement like this. So first, so when we need lock variable L1 and L2, so we first acquire L1, then it tried to attempt to access the L2, but it failed, then it release L1 also. So we can the thread will release L1 when it cannot acquire the L2. Okay, so by using this type of code, we can prevent the situation of no preemption. But this technique has the live lock problem. So for example, two threads could both be repeatedly attempting this sequence and repeatedly failing to acquire both lock. Okay, and so to solve this problem, we can add a random delay before looping back and trying the entire things over again, thus decreasing the odds of repeated interference among competing threads. So another problem is encapsulation. Okay, so in the encapsulated code, the programmer cannot release the resource allocated before calling the routine. Okay. So finally, so to prevent the mutual exclusion, okay, we can use a lock-free approach, while it is called as a wait-flow approach. In general, this is difficult because the code we wish to run does indeed have a critical section. To enter critical section, we must acquire lock. Okay, so to solve this problem, we can use some API such as compare and swap. Okay, so when we study the lock protocol and hardware primitive for a spin lock, so I introduced the compare and swap instruction. So using this instruction, we can implement the lock-free approach. Okay, so let's remind the meaning of compare and swap. It accesses some memory address. If the address value, the memory value is the same to expected, then it's success. Otherwise, it fails. Okay, and for the success case, the memory value is changed to new value. So by using this compare and swap, we can atomically update some data structure. For example, here we are to increment the value of this memory location, so to the amount by the amount. Then by calling this compare and swap, so this is memory value, and this is expected old value, and this is new value. Then this code will check whether the memory value is the same to old value. It's success. If this old value is the same to the memory value, then it's success, and new value is returned to the memory. But otherwise, it returns fail, and it will repeat this code. Okay, so by using this compare and swap, we can easily implement the atomic update operation of this memory. So we don't need to acquire the log and unlock operation. Okay. So this solution is very popular solution to avoid mutual exclusion. Okay. So using compare and swap, we can change this code like this. So in the first code, here, okay, so it first allocate memory and pointed by n, and it update the value, and using lock and unlock, it can implement the critical section. So here it change the head location. So this code is actually insert or linked list. Okay, so there is some linked list and head point to the first location, then allocating some new object, then we wanted to make link like this, then head pointing to here. So this operation insert an object into this linked list. So to update this list, we must implement this critical section using lock variable. But by using compare and swap instruction, we can implement the same operation without locking critical section. So compare and swap and the head and next and okay. So this code first check whether the head value is the same to and next is the head value read by this code. If they are same, that means there is no change in the head pointer between these two instructions. So in this case, head is changed to n. Okay. So, but this code will fail if some other thread successfully swapped in a new head in the meanwhile. Then in this case, this thread must retry this add operation, insert operation. So using compare and swap, we can eliminate this critical section code, and using simple atomic instruction, we can implement the atomic insert operation. Okay, until now I explained the deadlock prevention technique. So another technique is deadlock avoidance technique. Okay, so this technique monitor system state continuously, and it examines the resource allocation state, then let the system always be in the state that can allocate resource to each process in some order and still avoid deadlock. So in the deadlock avoidance method, the avoidance method will always keep the system in the safe state. So the system can be either safe or unsafe state. Unsafe state can generate deadlock, but safe state cannot generate deadlock. Okay, so the unsafe state has the possibility of deadlock. So, but the avoidance technique ensures that our system will never enter an unsafe state. This technique is called the deadlock avoidance method. For example, deadlock avoidance can be implemented by thread scheduling. Okay? So by scheduling thread in a way as to guarantee no deadlock can occur, we can avoid a deadlock situation. So for example, a smart scheduler could make two threads are not run at the same time if they might cause a deadlock. So let's see this example. So there are four threads, T1, T2, T3, T4. So T1 and T2 has the competition for the both resource of L1 and L2. So in this case, the scheduler serialized the execution of T1, T2. So these two threads are not scheduled simultaneously. Then there is no contention between these two threads. But T3 and T1 can be scheduled simultaneously because T3 require only one lock variable, and T4. So this scheduling, task schedule, can avoid the deadlock situation. For another example here, T1, T2, T3, the three threads access both two locks, so there can be deadlock. So in this case, three tasks are sequentially scheduled, but T4 can be concurrently scheduled with T1. So this task scheduling can avoid deadlock. So similarly, Dijkstra proposed a Banker's algorithm. So this algorithm also allocate a resource only when they cannot, even though the resource is allocated, there is no possibility of deadlock. Okay. So I will explain the details of Banker's algorithm in this class. Okay. But this deadlock avoidance technique is very conservative approach. Okay. So it may have been possible to run this task concurrently. So even though we execute this task concurrently, the deadlock will not occur. But to avoid deadlock situation, we limit the task execution concurrency, so it incurs high cost, high overhead. So this deadlock avoidance technique is useful in very limited environment and not widely used in real system. Especially this avoidance technique must know the pluralogy of the entire set of tasks. So this technique is not practical. So another method for solving the deadlock problem is to detect the deadlock, and if there is a deadlock, recover the system from the deadlock situation. So in this technique, allow deadlock to occasionally occur. Then if deadlock generated, then take some action when such a deadlock has been detected. Okay. Because deadlocks are rare case, it is better to use a pragmatic solution. So as you know, this very famous wisdom, not everything worth doing is worth doing well. Okay. If an OS froze once a year owing to deadlock, we would just reboot it when the deadlock occurs. Okay. So many database systems employ this deadlock detector, which runs periodically, building a resource graph like this figure and check it for cycle dependency in the resource allocation. In the event of a cycle deadlock situation, the system needs to be restarted. So this figure shows the deadlock resource allocation graph. So there are two processes, and there are two resource type R1, R2, and there are two items in the R2 and 3 resources in R1. So currently P1 has P1 used the 2 R1 resource, okay, and P2 is using 1 R2 resource, and it want to use another R2, and it want to use another R1, okay, and this resource is allocated for P2, and P2 also wanted to use on resource from R2. So using this resource graph, we can know that the resource allocation state. Okay. So to detect deadlock, okay, we can use graph reduction technique using the resource allocation graph. For this state, so here is there is a available resource now. So if this resource is allocated for P1, then P1 can perform its operation. Then it will release this resource. So resource graph is changed to like this figure B. Okay. Then P2 can use another resource, and it can use another resource. Then finally P2 can be completed. So all resource allocation graph can be reduced, then this is non-deadlock state. But this graph shows the deadlock case. So for this initial state, even though so let's see, there is only one available resource here. So if this resource is allocated for P3, okay, then P3 using the resource P3 can be completed. Then this resource is freed, and this is also freed. Then P2 can use this resource, and P2 must acquire 2 resources from R2, but there is only one available, so P2 cannot complete. Okay, so we cannot reduce. So if this resource is first allocated to P2 also, then P2 cannot be completed. So this graph cannot be reduced. Okay, so process P1, P2 are blocked in the state of in the blocked state in this graph. Okay, so reduction is not possible anymore, and initial state is deadlock. So this deadlock detection, after the deadlock detection, we must recover the system from deadlock. So to recover, we can use the technique of process termination or resource preemption. Process termination means the operating system will terminate one or more process to break the circular wait between the processes. And the terminated processes are restarted and rolled back afterward. So the terminated resource will release their resource also. Another technique is resource preemption. So instead of terminating several processes, only resources are preempted from some victim processes. Then the released resource will be given to other processes until the deadlock cycle is broken. So to implement this resource preemption, we need some election policy for the resource to be preempted, and the preemption reassignment of the resource must be implemented. In summary, so deadlock prevention technique deny a necessary condition for deadlock. So I introduced the 4 deadlock necessary condition: mutual exclusion, and no preemption, and hold and wait, and circular chain. So this deadlock prevention technique deny one of the necessary condition for deadlock. Then deadlock cannot occur in the system, but this technique require serious resource waste, so not practical. Deadlock avoidance technique need full knowledge of the entire set of tasks, and it must consider the worst case. Okay, so it reduces the resource utilization. So more practical technique is deadlock detection and recovery approach. It check whether current state has deadlocked, and if the deadlock is detected, then it recovers from the deadlocked state by terminating some process or preempting some resource. Okay, so until now I explained the deadlock. So in this chapter I introduced some bug types in real systems. So non-deadlock bug is more prevalent, but deadlock bug is also a very important issue. So to prevent deadlock, we must carefully design software. So there is a homework. Okay, so do the homework in chapter 32. It is related to deadlock problem. Thank you.